Hello to everyone.
Hello.
Hello across the globe. My name is Helen Gibson. I'm speaking to you from Melbourne, and I am a geologist and the Technical Sales Manager for Intrepid Geophysics. So we will now like to start our very first software demonstration webinar for 2014. I'm going to put you all on mute just for the moment, but if you did need to join or supply a message at any time, please use the chat space and we'll be on a lookout. So I'm going to mute everyone. Okay, now we'd like to commence. So here today we're going to be showing you GeoModeller 13, but I'd also like to say we're looking forward in 2014 to the release in March of our new software. So for today, 2013 will be the demonstration software, but right now I'll show you a PowerPoint and then we can proceed into the demonstration. So GeoModeller software was originally designed and developed some 20 years ago in France at BRGM, the French Geological Survey Organisation. And since then there's been many features and modules added, including geophysical modelling and advanced drill hole management. But now the development and commercialisation and licensing and support for the software has shifted to Intrepid Geophysics in Melbourne. But we still enjoy a strong partnership with the BRGM developers. So here I want to say something about the core design specifications of the software, and they're summarised here. The software is designed to incorporate a digital terrain model. It's designed to build complex models, including folds, faults, overturned strata, intrusions, and thin bodies. Also, it uses quite uniquely a 3D potential field method to interpolate implicit surfaces. Also, it employs rule-based modelling, which we're going to go on and explain a little bit about now. Finally, one thing that's important to the software is that you should be able to add and revise data and rebuild the model very, very easily. And so now perhaps the most unique and fundamental of the features of GeoModeller is the way that the implicit surfaces are built. And so it's done by a mathematical model, and we use primary geological data. So contacts are treated as belonging to isopotential surfaces, and dip and dip directions are treated as if they're describing the gradient or the field lines of a potential field. And by illustration, what happens is that what you're doing is coupling together the constraints from two related variables. Firstly, the contact data. So you can imagine here we're looking at a map. It may contain a green sandstone unit and a blue sandstone unit. So what we have here is the ability to construct the surfaces of those two geological units by using interpolation that couples together the structural data, which is not necessarily on the boundary of the geological formation. So now I just wanted to show a brief case study here where the Grand Canyon sequences are shown, and what I'd like to illustrate here is that in our last slide we showed just one simple example of the potential field method interpolating within one unit, but by using multiple potential fields and then processing the relationships between, we can begin to add complexity to our model. So note here we have some red lines which are separating units which are concordant, and between these we would have another series broken out, and then a separate interpolation would occur for each unit or each series, and then the relationship between would be processed afterwards. And those types of relationships pretty much in geology can be described in two ways, either as an onlapping or an erosional relationship. Of course, that we haven't discussed faulting at the moment, but that can be incorporated to add complexity to our modelling as well. So here what I'd like to say is that we talk about geological series. And so on the left-hand side we have a geological pile, and we've grouped together units which are concordant and separated those which may have an angular relationship between them. The first thing I'd like to say is that the stratigraphic pile is actually a model constraint. And so why is that? Hopefully this slide will illustrate that point. It's because you can see on the left-hand side, for the top of the yellow unit, we have a blue series which has an onlapping relationship. And so you can see on the left-hand side that this model is created as onlapping, and so the blue is going to stop against the yellow. And just by changing one part of the geological pile, this is the erosional contact now introduced, the model now becomes quite different as the blue units charge through the yellow units below. And this is why we talk about rule-based modelling in terms of the stratigraphic pile. Many things about the pile are, of course, constraining the model in terms of the order of the units and so forth. The typical way we talk about Younging direction within a pile. So the pile is editable, and it's certainly a model constraint. Now I'd just like to show you an outcrop map which contains field observations. Of course, there are many ways to import data into your model using external file types, but here I'd like to show the way that you can actually digitize directly into your GeoModeller workspace. And so this next slide is just to show you that we have an image manager in GeoModeller, and it's similar to many other GIS packages. So what we would need to do to build this simple model is to first have created a stratigraphic pile, and also it's important to choose to work in either tops or bottoms. If we just think on that point for a moment, by intuition we know that the bottom of the blue unit is the same contact as the top of the upper pink unit, and because we can say that it may become confusing in terms of importing your data and thinking about that contact as either being bottom of blue or top of upper pink. So to avoid confusion and to allow GeoModeller to organize the data, we always build a model either in tops or bottoms. And although that's editable, you wouldn't normally change that definition once you begin modeling. So the process here now is to pick up the Create tool and simply to digitize your geolocated outcrop map, which is in the workspace of GeoModeller. So here we're digitizing two things. We're digitizing around the units on their contact, and secondly we're digitizing faults, which you can see here through our outcrop map appear as a west-east trace and also a north-south approximately a trace through here. So we have the understanding as geologists, we can see an anticline here, and we know that there's a Younging direction towards the south west. So we can begin also to digitize the orientation data, and that then takes on a full 3D reference position. The result of our modeling here is shown on the right-hand side with the raw data shown on the left-hand side. So just remembering what we talked about at the beginning of the PowerPoint in terms of that we have a mathematical model here, and it's coupling together the structural data with the contacts, and we're creating a curvy linear style of building an implicit surface. What I'd like to point out is this is pretty good approximation of nature in many ways, but you can also do some very sharp style modelling also. So just to point out what's happening here at the fault traces, if you focus now on the pink line coming through, you can see that the field lines are tracking along, and then there is a break across the east-west fault here, and it starts up again on the other side. In GeoModeller, I'd just like to point out that you never actually say what the throw of that pink unit is against the fault. It's just fundamentally defined by the way you see the contacts tracking up to the fault and then starting again on the other side, and this is the fundamental way that we produce throw on a fault. So here is our final current model. I'd just like to point out that there are infinite faults here as they go all the way through the model. This one is also infinite, but it does happen to stop on this fault. So now we're going to talk about the building of fault networks, and this introduces the second way that we say that GeoModeller includes rule-based modelling. So why are fault relationships also a model constraint? This is because you can set up rules, and in GeoModeller we do it by two matrices tables. First of all, we say which series is going to be affected by the fault, and then secondly we say which fault is going to stop on another fault. We have a simple network here, just two faults. So once you tick on that the blue fault is going to stop on the green fault, there is nothing more that can be said because the other areas are grayed out. Once you begin a lot of complexity, you can have many, many faults, and this becomes quite a complex table of relationships, which is all handled by the GeoModeller software. So just to look at our current model, which is built with infinite faults, you can see that the blue fault is stopping on the green fault here. What we've done is just strip away everything bar the basement unit just to see the relationship, plus to be able to show these fault planes. I just want to point out too that fault planes are built by the interpolators in the same way, and so as units, which means that you can build actually very, very complex planar surfaces, even though these ones are here are quite planar. So now I want to introduce the idea that we can change these to finite faults. And so on the left-hand side, we're just exploring the fact that as an infinite fault in a model, you will have constant offset of the unit in every direction away from the fault. If you were to introduce, though, a definition whereby for the affected series there is the maximum amount of offset at the focal point of the fault, and then a dissipation away towards the zone away from the zone of influence of the fault. This is what we can do in GeoModeller, and we can set these up using an invisible ellipsoid. And how I'd like to explain this is to say that we have three axes in which we need to set up. These are the radii values of an invisible ellipsoid, which is going to clip the plane of a fault that we make. So here we have vertical or horizontal and a third axis of dimension. And this, the other thing we need to do here is to say where the origin of the ellipsoid is going to be located. On the right-hand side, you can see that this is quite a tight envelope in which the influence of the fault is going to occur. And you can see just in 2D, although it's a 3D model, just presenting the 2D render where this fault plane is clipped by the edge of the ellipsoid. And so now just to return to our mapping little project, you can see the green fault here now is limited. You can just see the definition of a sphere here, which is interacting with the basement unit. You can see maximum offset is in the central part of the sphere, and you can see that there's a dissipation of the offset of the fault occurring out towards the edges. So no longer is the blue fault seeing the green fault as it comes past, and so it can continue. Even though it was set to stop on the green fault, it no longer sees it. And likewise, in the foreground, we have this section which previously was offset by the green fault and no longer is it there. So these next two slides, I just wanted to introduce the possibility and the extra features of GeoModeller, and to say that you can load drill hole data, and of course these become like a contact point. Any drill hole intercept also becomes a constraint of the model for building the geology surfaces. The other thing you can then do is load numerical data down the drill hole of any variety. So we may be talking about gold assay data, or we may be talking about densities of different geological units. And of course, the reason to do this is to perform a 3D kriging of any type of data, and then therefore mesh these results in 3D. Also, and just if this is my final slide before we commence the demonstration, I'd just like to show you another case study. This is from the Brockman Syncline in Western Australia. So we have some banded iron formations, beautifully folded, and you can see those on the left. And knowing what we now know about the definition of faults in GeoModeller, you can see this red fault is set to be a finite fault in the model, an infinite fault in the model, pardon. Plus we have a combination with some finite faults, and also these little brown faults in here, they're set as stopping on relationships either end. So this is the way we can introduce complexity. Of course, this is just a 2D rendered view of the surface topography, and but it is a 3D model. On the right hand side we have the total magnetic intensity map. And it's shown geolocated below the modeled lines for geology and faulting of this model. And you can see that there is a very good correlation here with the geology of the magnetic intensity. And so you may just want to choose to do some work inside of GeoModeller Workspace just by digitizing and doing your interpretation. And perhaps you wouldn't choose the TMI, you might choose the first vertical derivative, or you may choose the analytic signal map. There are many ways to work directly with your data in GeoModeller. And this is aside from other workflows which you can continue on after your initial model is built, whereby you may want to improve the geology based on forward modeling and inversion of this geophysics data. You also have the possibility to add knowledge about geological uncertainty through the use of geophysics. GeoModeller also has the ability to perform multi-scale edge detection of geophysical data sets, and this would be done for the purpose of having a way to automatically do a structural analysis to add to your knowledge of your fault networks in any area. And I didn't mention that property optimization is also another feature of GeoModeller, so that if you didn't have a lot of observations of density or magnetic susceptibility, you can begin to do some solving of those types of values. So at this point I'd like to say we'll move on to the demonstration, and let's see how we go from there. I just want to say at this point that we're going to have time at the end for questions, and perhaps this next section will take about 45 minutes. So here we go. What we have is a model which is slightly advanced from just the start point. If I was going to start a new model from the interface of GeoModeller, which we can see right now, under Project, I would go Project New. But rather than start at the very beginning, which is just takes another 15 or 20 minutes from this point, I want to start here to show you the project properties. And so this is a model of Mansfield in Eastern Australia. There are a couple of important things to point out here. One is that it's a projected model, so it contains a proper projection system, GDA 94, MGA zone 55. So all of our data sets coming into the model have a proper geolocated position. The other thing that's previously been set up is the project extents, and you can see this by the wireframe. And what we've set up is something that's 17 kilometres by 17 kilometres by 3 kilometres in the Z direction. If you were to now have a look at this wireframe, you could notice that there is a topography surface in here. So let's have a little bit more of a look at that. When you load the DTM into GeoModeller, it takes a copy of it at the resolution that you choose to resample on the way in. And if I'm just going to visualize that now and have a look at our grid, which was retained from that process. So you can see we have a proper surface in here, which is representing, let's have a look. Needing to move my tool, that's better. So in 3D I can choose to vertically exaggerate, and we can see now that we have a topography surface, which is a special type of 2D section in GeoModeller because we can add data to it, but it's actually a non-planar surface. And just to show you too that the grid is kept in a state which is still able to be analysed, here's a histogram of all the elevations inside of the Mansfield DTM, and so you can see that it has elevations above sea level which range between 214 metres and 775 metres. Okay, I will just hide the view of the grid now, and I'll also return the model to normal exaggeration. The next thing I want to do is to show you that we've just done the one thing here, which is to load a map using our image manager. So you can see this is now on our surface topography section, and if I do a mouse wheel, you can go in at higher magnification and see that it is the Mansfield map as published by the Victorian government. Now, as I move my mouse around this map section, you can see down, perhaps you can see in the left-hand corner, there are some numbers which turn around. So obviously the X and Y, which is equivalent to northing and easting, they're moving around as I'm doing a mouse wave on the section. But Z is also moving around, which proves to us that this is a true topography section. It's not a flat 2D image. So obviously we have now the task to begin to build our model, and let's do that firstly by seeing that the map contains some orientation data. So somebody has done some digitizing here, and if I just pick up the pan tool, for example here we can see that there's a lot of data on the map, so I could digitize directly, but the choice I'm going to make is to show a whole range of different ways to import data. And the first way I'm going to show is to show how to bring in some orientation data using our CSV importer. If I load to the file now some of our data, from the upper Mansfield, I'm going to choose to bring in the dips. So this importer is looking for 5 columns of data, and now you can see these, I hope. There's an easting, a northing, a dip direction, a dip angle, a polarity, which means either overturned Younging direction or normal Younging direction, and then a geology identifier from which unit the data belong. I'm going to go fairly quickly through these wizards because they can be time consuming, but the idea is to check that each label is mapping correctly with the columns. So I'm just going to proceed, and the idea here is if you had a very high intensity of data, you may choose to have an averaging effect on importation of the data, but we're just going to proceed here to import the data. The idea here is that we haven't already set up a formation, but I'm going to do that right now, and of course it's identified the label in the data in the fifth column indicated we're talking about orientation data from the Upper Mansfield unit. So now the idea is just to finish, and it just gives a report to say that 35 pieces of dip and dip direction data have now come into the map. So that's our first job done. Coming across now, we're going to import drill holes into the 3D viewer. So let's commence on that. Again, from the upper menu, it's import drill holes. These are arranged in 3 files. I'm firstly going to browse to the collar table. Second one is the survey table. And the third is the geology table. Again, it's a matter of parsing and then mapping the columns, and I'm going to move again quite quickly through these. Just to see visually though that what we have here is a whole number. So we have 10 diamond drill holes coming into the project. Each of these, because we're actually looking at collars at the moment, the collar has an easting and a northing and a collar height, and then a total depth of the hole. So moving quickly, just so we can get to where we want. Now this one is a problem. Of course, a problem meaning that your data won't necessarily be perfectly arranged, and so you will need to use some of these text qualifiers. And for instance, I can see that there are single quotes here. So if I tick this box, it's going to jump correctly to saying, oh, now I understand what the column labels should be. And the last page of the second last page of the wizard, we're still parsing. This time it's the geology, it's the from and the to depths. If you needed to do a unit conversion, you could change feet to meters at this point. And also there may be some errors that in terms of intervals, if there's some overlapping intervals, you're going to see this reported. Now on the final table of the wizard here, you'll see that it already knows about the Upper Mansfield because it already contains the orientation data. So, but for these 3, it's found new geology labels which need to be added to our geology objects. And so above the line, we can create formations that don't already exist. Also at this point, you can have the choice to go in and choose the color of your liking. And also make, or otherwise you can make those color choices in another part of the menu. Let's show the drill holes after we finish importing them. At this point there will be a report. Some of the comments might be that you have some intervals which are overlapping or missing, and that would be fine to proceed, but it's just a warning if you need to troubleshoot your drill hole data sets. And so here we can see them now in the 3D viewer. So really what we have is the very minimum amount of data which is now possible for us to build a model. We have contact data by virtue of the drill hole intercepts. That's one and the same. A drill hole intercept is literally considered to also be a contact point. On the left here in the 2D viewer, we know that we have some orientation data, but we haven't built a pile yet. We do need to have a stratigraphic pile to arrange things because that is another model constraint, as we now know. So going into geology, I can create the stratigraphic pile. I'd like to choose to build my model in the bottoms of the units, so I'm going to select bottoms. I'm also going to select new series and arrange these as I need them. So you can see that each of them are going to pop into the right-hand list as I need them. Bringing across, I also may want to reorder these. Perhaps they've come in a different order. Upper, middle, lower is correct though in this case. Also we have an onlapping relationship with the series below, so onlapping stays this way. If I change this to have a name of my choice, I'll just call it the Mansfield series. and I can commit that change. The next one that's popped into the list is the last of our possible formations, and this is basement. So I can literally just choose it to be also on-lapping, because the bottom of the basement is actually below the bottom of our model. So in some sense it doesn't matter what the relationship of the bottom of the basement is to the model. Here is our place to just verify what we've set up, and that what we're saying is that the upper, middle and lower Mansfield are concordant units, and in effect they can share structural data. So let's proceed on that basis. Now we're just going to check what the pile looks like, and we know that we wanted to set bottoms for reference. We also have upper, middle, lower Mansfield in the correct order with an on-lapping relationship to the basement. So we can do a save at this point. And the next thing I'd like to do is to commence to build our very first model. So the idea is to compute. We're going to select to compute the Mansfield series because we have data in that series. We're going to select to take all the data into account which lies on the surface topography section, and we're going to include all of the drill holes. And so let's proceed to say OK. Now, a compute has been done, but you may not know it because there's nothing here to see, except for the fact that the mathematical model has been solved, and we're now in a position to be able to render out the results of that mathematical solution for all our implicit surfaces. Just firstly to show, we want to plot the model on the 2D viewer, just showing lines for the first instance, and say OK. So here is a construction really of our first geological map of the area. We can be relatively happy with this. We can have a look here at our, let's say we want to select a drill hole. We can do this directly off the 3D viewer. Now that I'm touching this one, I can see it's diamond drill hole number 1. I can edit that and have a look. We can see we have actually built an almost perfect model which honours the drill hole data, and this is easy to do because the data is quite sparse. It's very easy to build a very nicely fitting model with sparse data. And so on the right hand side you have the model itself, and on the left hand side you have the actual drill hole trace. There is an ability to do some editing at this point. You can also choose, for example, if there was something wrong, you may have made a mistake, and in fact all of this unit belongs in Middle Mansfield. There's quite a bit of editing we can do at this stage. If I was to make changes in this drill hole dialog, I would need to save the changes, but since I don't want to do that, I can just close and it will go back to normal. The other thing that may be useful here is that you may want to do what's called relaxing an interval. And this means that if I am unsure about the location of the top of basement in this drill hole, a grey line has appeared because I've said I wanted to relax that interface. And this means that next time I go about doing a computation of the implicit surfaces in this model, it would not include this contact in the computation. It would relax that interval, which would allow you then to model using all of the surrounding drill holes but not this drill hole, and then later on you could imply a new constraint which may be a better guess than what your original drill hole log is available to you. I'm just going to close that now and click outside to continue on. The other thing you could do at this point in time is take a new section and build one of those. So if I take the Create tool and click on two places roughly east to west, I can make a section. And when I do that, I have the ability immediately to render it to in 2D. This time I'm going to show the fill on the section. So here we are. It's our first geological section, and it's already available to us because the model is computed. I haven't changed anything to do with that drill hole because I didn't save the change. If I'd like to put it across in 3D now, it's possible to do that. And so now we have a composite model with raw drill hole data and also a section here from the model itself. So if you want to actually continue with this theme of building some sections, one very important thing is that we may want to look at the drill hole section, something that's closer to that location. So if I go Model, Project Data and include the drill holes, you can see that I have the possibility to see those in the location here where the collars lie. So this time I'm going to take and create a section more closely through the drill hole collars and create a second section. You see straight away a wireframe has been set up and it's ready to have the new section created. The first thing you can do also is to project the drill hole data onto those sections. So if I choose some number of projection, like 1200 meters, I can project all of the drill hole data to this section and have a look at it. And then I can compare the drill holes against the model, the current model like this. Okay, so and finally to put that across in 3D. I'm just putting the lines across in 3D this time, so you can see that there's a bit of flexibility here in how you want to work with things. I won't go on any more about drill holes because I think it's a really good topic. It's a big topic and we can have a whole separate webinar on it in a later month of this year. What I'd now like to do is to return to our map and see, well, actually we still have some work to do here, because if we look in detail at our field mapping, we haven't so far contained very much of our outcrop data to say that the syncline, although we have the sense that there is a syncline in here, we need to honour the contacts a little better than what we have. So now I'm going to show 3 more ways to bring in some data to improve our model. And the first of these ways is a digitizing way of importing. So I'm going to pick up the Create pencil tool and digitize around the eastern limb of the Mansfield syncline, knowing that this upper grey unit is called Upper Mansfield. And if I mouse wheel in, you can see that we're going to stop here just before the fault because I want to include those faults later. When you have some digitized points, you can create the geology data now and make sure you're putting them to the right geology object, which is Upper Mansfield. And I can leave that dialog box on while I continue to go now up the eastern limb of the syncline. Something like this. Of course, I'm doing it very fast today, but in reality you would do this a little bit more carefully. So here I think if I just turn off the map, you can see that my new data exists here. And I'm just going to turn off the model, so we can see the raw data. So these are new contacts created by digitizing, and just to make a point that the lines between the contacts actually don't mean anything to GeoModeller. They are just a linkage which allows you to manage the polyline, but they are not used in the computation of the implicit surfaces. So that is the demonstration of digitizing. Now I would like to import by a second method. And this is a more simple structure for the file. It's a .data file. And so we're going to bring in the contacts for the middle Mansfield this time. And straight away you can see they've come here and straight away into purple. There's a bit of a crossing problem there because I was lazy. I didn't look very carefully. So I'm going to take my Move Points tool and move these out a bit because I know that's not a crossing relationship there. That's actually not correct. So there we go. We've moved the points individually into a more correct location. And then finally we're going to bring in by a third method, and this time we're going to use the GIS importer. So if I now browse to the file of interest, I'm going to pick up out of the GIS data something which is a shape file. You could also, there's many different, there's ArcGIS files and there's map info, but we'll just pick up this one. It's an ArcGIS file. It's actually in latitude and longitude, and so this is obviously not quite compatible yet to come into our projection system here for Mansfield that we've already set up. So there's going to be a conversion on the fly as we import this data. So let's have a look at it now. Having pressed that button and commenced the import, we now have a status report. And this says that it did recognize that a datum conversion was necessary, and this has been done. It's also recognized that the file that I imported contained 46 polylines, but only 5 of those existed within the area of our model, and so it was necessary to clip all of the others but just bring in the 5 polylines which exist within our project area. So we just can say OK to that. And now actually have a look at the data that's now available to us. This is what we call the points list editor. These are points which exist in a transient state until we're ready and know what we want to do with them. I'm not sure if you can see, but we have a green line out here which exists from our data set here. It's polyline segment 1 of a possible 5. And as I click through the segments, you might see I've moved on to polyline 2, polyline 3, and so forth. And you can see them moving around because we have choices here about which one we want to import. Now the one that I'm on right now happens to be the bottom of the Lower Mansfield, and this is the one I'm interested in. However, we can see on polyline 1 now, having this one up for choice, that there are 70 points which comprise this polyline, and this data would tend to be a little bit too rich. We don't want to slow the computation down too much in GeoModeller, and it's slightly unnecessary at that high resolution. So I'm going to thin the line down by using threshold filtering, and this is the sliding bar up here. So if I take this across all the way, we can thin the line down to 15 points. Now that's a little bit too rough. So I'm going to bring it back halfway, and you can see now I'm on about 43 points, and that continues to maintain the smoothness of the line, but it also it's done an intelligent thing. It's left more points in. If I go actually through the points one by one now, you can see it's left more points in around the areas of high curvature. So it has thinned the line in an intelligent way. I think we're ready now to commit it, and all we do is go over to the Create Geology Data area and commit it to the Lower Mansfield and push Create. Okay, so we can close now the GIS editor, knowing that we've now got some better constraints on surface for our model. So what I think I will suggest is that we do another project save. And afterwards, what's going to happen is that we're recomputing the model. So to do this, I'm opening the compute, I'm selecting the Mansfield series again, I'm selecting all of the sections which have data on it. In fact, we created these 2 new sections just to have a look at our model previously, but we didn't put any data on them yet. If we had, we might want to choose to select them and include that data in the computation. But either way, it's not necessary. And also we want to take all of our drill holes into account again when doing our computation. But you have the choice to exclude some drill holes if you prefer. So going on with the computation, that's now done again. The mathematical model has been solved. And to do a render now, I'd just like to show the fill, and this time we have something which looks a little bit complicated only because I haven't taken the care to build this very well, and I think it's the issue will be to do with the way it was digitized quite roughly. But I guess what I'd like to say here is that we are beginning to honor what you can see is the more complex syncline. So a little bit more work to do, but nonetheless, what the constraint actually could need, and I think we will do that now. Let me just erase that model. I think what could be necessary to understand is that we need some more orientation data, because that will help constrain the model out here through the western limb a lot more, because of course it was free to build any sort of shape. So this time I'm going to import some more orientation data, and so let's have a look at that. This time we're going to browse to Middle Mansfield dips, bring those in so you can see some more orientation data, and finally the Lower Mansfield. Lower Mansfield dips. Okay, now this should constrain our model a lot better as we're adding more data. So let's have another try at that computation. And again to rebuild. Okay, now that's coming to be much better controlled, and that's not at all surprising since we're now introduced quite a bit of surface data from our map section. What we can do now is have a look at the build in 3D. And here's our first 3D model. So it's on the right-hand side, and what I can do is remove the layers. You can see now there's a little plus sign here at the 3D model area, and I can expand those and hide certain sections at any one time. So here we have the model with a composite view showing the drill hole data as well. Also, I can choose to have a look at my sections and again put these across for viewing. What I'd like to proceed to do now is introduce the faulting, because there is some fault network, a small one on the western limb. So just to erase that model data now and bring back our map, you can see we've got two faults down here in the western limb, and I'd now like to add those to our model. So the first thing to do is to add them as a fault object, and we give them a name. The first one I'm going to call Vic Fault, and give it a color that's easy to see. And there is a second one, so I'm going to call it Vic Fault 2. And close that. Now, of course, it's asking me, oh, okay, we have some fault data now. Would you like to link it with the series? This is the first of our two matrix tables, and remember, it's available to us because we have rule-based modeling to do with fault networks. I'm going to set the Vic fault, both faults actually, to interact with both the cover series or the basin sequences as well as the basement. And so that's all I need to set. And now I can actually define those. If I pan and zoom, I'm ready to digitize some faults. If I take the Create tool, I'm going to call Vic Fault 1 is the more southern fault. Actually, I might not start out there. I'm going to bin those points, starting again. So I'm digitizing the trace of the fault. Just 6 or so points will do it. And then as soon as that's done, I can go up to the Create Geology data list. And notice that you also have the faults in the same area. So I'm going to choose Vic Fault to be the recipient of those 6 new points. Now I'm going to digitize the second fault, Vic Fault 2, and find it in the list. Create. Okay. Now, of course, we're building a separate implicit surface here, and so the two fundamental things you need is both contact data and some orientation data. That's the minimum to do a computation. So I could simply build some piece of orientation data for the fault, which might be here alongside, and to do that I would click twice and go to this tool this time to ask to make some fault data with a dip direction and a dip angle. That would be creating them one at a time. I'm actually not going to do that because there's a better way, a faster way in this case. And that is that for every place between a contact point, I'm going to ask to make some orientation data which is associated with the trace of that line and orthogonal to it. So let me have a look now to edit this fault trace and turn on associated orientation data. For this fault, I'm going to make it dip towards 45 to the north. Let's have a look at how that turns out. If I turn off the map now, you can see that I have these little ticks here which are indicating a dip direction 45 degrees towards the north. So that is exactly how I would like them to be. What happens is you get a left-hand directional creation of those ticks. If I was to switch the point direction, which I can do, flip order of points, you see I can reverse the direction in which the orientation data automatically created, and I'll flip those back again. So let's have this little fault network with an orientation dipping 45 to the northwest, and it's going to actually intersect with Vic Fault 2 further north. So I'd like to select that now and likewise edit, but this time it's going to have an associated dip angle of 90 degrees vertical. Now it's more difficult to see that I've added data for this case because as you steepen up the angle, GeoModeller makes the symbol smaller. So we're not surprised that you don't actually see that this one is vertical dipping. So I'd like to save at this point again. And now what we will do is do a new computation and see that the faults have arrived in the list, so we are able to select them now in terms of our computation. Let's have a look at our first model. That's right. So here we have it. Red on red doesn't work too well, but we have the two fault traces coming through here. And if I was just going to build these in 3D, I just might want to see them. First of all, you can choose just to work with faults alone. So let's just do that, a computation in 3D of the fault surfaces. You can see them here in 3D, and I'm just going to make them shaded up. So this is almost what we want, but not quite there yet. There's two things here to make it fit best with our mapping. One is that we obviously need to limit the faults. So that's what I'm going to show you now, as to how to make limited faults. The second thing is that in our knowledge of the region, we know this to be a little splay fault, and we would have expected that Vic Fault in the south would stop on Vic Fault 2. So we need to turn that on in our matrices table rather than have the two faults go through each other. So first of all, we'll turn on the link faults with faults, and we're going to ask Vic Fault 1 to stop on Vic Fault 2, and with a matrix of just 2, that's all you can do, and say OK. Now the second thing to do is limit those faults, and remember we're setting up 3 different axes of our invisible ellipsoid, which is going to clip the plane. So I'd like now to well, do one thing in preparation, and that's use the tape measure to see how long this trace is. With the tape measure, you can see it's roughly 2.5 kilometers long in the trace, and that means what we need is to have a radius of half of that. So let's proceed now. In attributes, you select the Vic Fault and change it to finite, and now I'm going to put in 1200 meters radius. So it's actually an invisible sphere to cut the plane. What's going to happen is that we have a choice to locate the origin of this ellipsoid central to the area. There are other ways, though, to define the invisible ellipsoid's location. If you just now go OK, and we'll do the same for this fault here. One to the north. I'm just going to make it the same. 1200 meters is the radius of this invisible sphere to clip the planes. Again, to do a computation of the faults only, we go OK and build in 3D. So now we have it. We've proceeded to get pretty much what we wanted. We wanted a clipped fault plane, and we wanted the two planes to intercept, but we needed the southernmost one to stop against the more northern one. So if you can see the viewer now, this gives us what we wanted. So let's have a look at the whole model together now. There will be some issues, and I'll just point those out straight away. Now notice that if we bring our map back, we would have had some things to fix here. See how the units, they don't go like this. We need to cut and change some part of this definition. So let me just do a simple fix. What happens is we're going to break the polyline using the split apart tool. There, and we're also going to move that point to make it exist just inside this fault compartment, and again I'm going to use the split apart tool. So now we have, you see the process. We're going to split the units so that they can actually interact with the fault correctly in the way we normally think of as geologists, like this. You may also want to build a little bit more information here, so again I'm going to pick up the create tool and put something here for the upper Mansfield. Okay, we have a couple more points. I think this will be better, and we'll just save that work. And again, do a computation. This time we'll include all the faults and the formations and all the drill holes. This time in 2D. You can see that we have much better representation of what we needed, and also we have not quite the ideal, but it's working here through the units here. I needed to move this one to get more of an expression of the fault working. Let's have a look. And that's a little better. I think I need to just check too that the faults are linked with the series, which they are. Okay. So there's a little bit of tidying up to do here, but you can see that it's working in terms of breaking the units going across the fault here in this way. Now just to finalize, I just wanted to remind ourselves that we're working with the potential field method, and so let's have a look just for a moment now to build this model in another way. Rather than show the fill, I'd just like to show the fill for the basement and not show the fill for the series, for the basin series, and let's have a look here. So this is to render out what we call the field lines. These have a use. The field lines are what the potential field method is displaying in terms of the gradients. And so these are useful. They can be reused for instance, hydrogeological modeling. FeFlow can take in these types of values because they can make use of an anisotropy angle for flow lines. And another place where GeoModeller can reuse these types of field lines is in what we call domain kriging. And this is one part of the the advanced drill hole module, whereby you may want to Krieg some values, let's say some gold assay values, and you may want to have them do a special type of Krieging which takes into account the shape of the geology. If you had some very complexly folded host units to a gold deposit, you may want to, rather than unfold your gold deposit, then do the Krieging of the gold assay grades and then fold it back again. Domain Krieging can make access of the field lines so that you can have a possibility to not do the unfolding prior to Krieging. It does improve the Krieging results. So that's just to show a little bit about what's special in GeoModeller, and that brings now together the closing stages of the demonstration today. So what I'm going to do is, while question time is on, I'd like to return to our PowerPoint because there are some further bits of information here to say what's next after today. There are two things possible. One is, well, there's three things possible. This webinar has been recorded, and if you'd like to see where you can see the webinar again, we just contact us by email. The second thing is that we have a Google group starting up as of today where we can answer additional questions that we haven't had time for today. So the instructions are here on your screen now. You may want to take a screen snap of that. And finally, we do offer free 4-week evaluation licenses for GeoModeller software, and so there are also some instructions on the screen now to show you how to do that. But from our end, we're going to throw open to questions and see how many that we can do in the time. So I think what I'd like to do is if you have a question, probably the best thing to do is to type it in your chat dialog box. And as I see those, I will be able to unmute the person asking the question. So please ask away. Thank you very much for your time. If I'm smiling now, it's because Richard Lane has left me a message earlier on today saying, "Don't look so worried." I have a question that we should make a link of this recording and perhaps even email it to all the attendees. So yes, we can certainly do that. I have a question from Pauline. And Pauline is asking, how would you integrate a groundwater table into this geological model? It's a complex answer really, because it introduces the possibility of a couple of different workflows. GeoModeller is making improving on our interoperability with flow modeling codes as we speak, but our first way to do that is with FeFlow, and we can at the moment fill the centroids of a pre-existing FeFlow mesh and also bring in those anisotropy angles from the field lines, which is something I think I've introduced a little bit today. So the workflow is available if you are using FeFlow as your flow modeling code. Now the other direction we're working on is we're soon hoping to have better interoperability with MODFLOW, which is an open source USGS code, together with a plugin. I think it's called no, it's gone. Let me post that one on the chat space in our Google forum, but there are some ways we can work with MODFLOW, and certainly we're going to improve those through into the future. We have a scheduled finish time in 3 minutes, so just in the wrap-up I'd like to thank everybody. It's been a very good turnout. We've had more than 20 people log on, and that's very pleasing for our first one for this year. So I look forward to keeping in touch, and that will be a great way. Let's start chatting on the Google group, and we'll be in touch again in the middle of February for the second round. Thanks again. Yes, Richard Lane has mentioned the heat here today. I'm all ready for summer. We've got our second day of 42 degrees Celsius here in Melbourne, so I hope you are all in a cooler place than me.
Sonido reactivado.